go ahead and get started. And I'm going to talk about sparse matrices today, and in particular sparse matrix vector multiply in a little bit of detail, and talk about various ways in which optimizing them is different than optimizing dense matrices, which you have a lot of experience doing, especially for dense matrix-matrix multiplication. And just to give you a little heads up, the plan is that next time Jim is going to lecture on structured grids, but he'll also spend some time talking about project ideas. If there's enough time, I'll throw out a few project ideas today. You should be starting to think about what you want to do for your project, looking for project partners. The Homework Zero postings are up. Those are not a commitment that anybody's working on that particular project, but just to give you a sense of who else is in the class and what their interests are. The other thing I think we will do on Thursday is have a, I think Ben will probably talk a little bit about Homework 3. So as you're wrapping up Homework 2, it'll either be Thursday or Tuesday probably to get make sure people are ready to work on Homework 3. I realize it's been a while since the UPC++ lecture. And in that lecture, I talked a little bit about genomics, but that's what the homework is going to be about. So has anybody started Homework 3? You wouldn't. Oh, okay, all right. People have at least looked at it. People have looked at it. Okay, good. That's great. All right, so what are we going to do today? Actually, I'm going to start with some other homework. I'm going to start with Homework 1 results, and I don't think I see Grace here, but she did the processing of these, so I'll talk a little bit more about, so the suspense is building. You'll get to see how everybody did on the homeworks. No names are attached, of course. And then mostly I'll talk about sparse matrix stuff, and I won't read through the outline. Okay, so what does it look like for Homework 1? Well, so this is the serial part of the homework assignment, and you can see there's lots of different sizes that are tested for both, as you probably did yourself, but anyway, both powers of 2 and non-powers of 2, minus a power, a power of 2 minus and plus 1, which gives you a pretty jaggy sort of performance numbers. So hopefully that's what you're used to seeing. You can see though I mean, in general, I was very happy with this. I think people were up here over, generally they got some numbers at least over 40%, 50% of peak. The y-axis, I should say, is percent of peak, as you probably know. There is an outlier up here at the top, so you may be curious about which group that is and what they did. I won't tell you which group it is, but I will give you some idea of what they did. So as I said, Grace has read all these homework assignments, and so the summary is basically everybody in the class did blocking, not surprisingly, since we told you to do that. Everyone did some kind of SIMD optimization, so that was also not a distinguishing factor, but it was important for people getting up at that sort of 40% number. 90% of the teams did some form of memory rearrangement, either a copy optimization of some kind, some padding to get the, as part of the copy optimizations, they padded the matrices, and they may have done some kind of packing of say, a sub-block or something like that. And 73% explicitly aligned their blocks with, did memory alignment. 65% did loop unrolling. I know that some of you may have tried it and didn't include it. I know sometimes that can be a little bit counterproductive, but and about the same number, 65% also explored different compiler flags. So of course I'm not telling you for each one how that changed that graph that you just saw, but you get a sense of kind of what happened. 85% tested performance on a different machine, which is great. So hopefully you learned how the performance varied across the machines. 15% of the teams tried to do some kind of manual prefetching, and for most of them it was a waste of time. It didn't actually work, but for a few of them it did. So I can't tell you exactly why. Maybe Grace could, or maybe, I don't know, anybody in the room want to say how they got manual prefetching to work if it didn't initially work? Nobody really wants to share that detail, but so it did. There must be only a few of you that actually got it to work. But anyway, and the team with the fastest, that outlier at the top, did a little bit of hand-tuned assembly code. So that's the difference between the standout one at the top. And I don't know for sure that it's the same, but I was going to ask Grace. I suspect that's also the same outlier here. So there's the OpenMP code, part 2. So percent of peak here, not quite so good, obviously. So we've got a lot of codes that are down here at the under 10% of peak number. I mean, it is a lot harder, obviously. I mean, even the best case for the largest sort of matrix that we tried it on, we're getting up, you know, a little bit over 50% of peak, and so, but this was obviously a lot harder for people. So some notes about this: the test sizes were pretty small. You could see generally all the numbers were going up there on the right. Well, not all of them, but for many of the teams, you know, you might have done even better out here a little bit, so the matrices might have been a little bit small. The low performance numbers that we see in a lot of them was often due to excessive synchronization. So this is something to think about when you start working on, well, you've turned in your homework too, but also as you start thinking about your final project. When you're writing OpenMP code, it is really easy to accidentally serialize your code and accidentally synchronize your code. So you've got to have, you know, if you've got some kind of a OpenOMP pragma critical that gives you a critical region, it may seem like a little bit of code, but if it's not very much computation that is embedded in, you can really spend a lot of time doing that in those critical regions, and so that's serial code. You're going to kind of also spend a lot of time in OpenMP going in and out of parallel loops and things like that. The copy optimizations can help if multiple threads are fighting over a cache line. So I think I talked about this hopefully phrase when I was talking about architecture a long time ago now, but it's called false sharing, where you've got two different threads that are trying to share the same cache line. It's not a problem if it's read only. If neither one of them is reading it, both processors will get a copy of that cache line in there. The cache that is the level of cache that is the level 1 cache, which is per core on any of these architectures. But the problem is if either one of them starts writing it, then some kind of synchronization protocol down in the hardware has to go on in order to make sure that those writes are visible, that the cache lines are coherent, that they're visible by both processors. And so with false sharing, although if the hardware is behaving correctly, as it should, and these processors, I don't think there are any bugs like that, but if you're both writing to the same cache line, or one of them is reading, the other one is writing to that cache line, it's going to bounce back and forth essentially, or something's going to happen to make sure that the values are being kept consistent, even though you're writing to different parts of the same cache line. So that's something else to be aware of if you're writing OpenMP code. You know, this is kind of one of the reasons that sometimes partitioning your data structures, as you do in, say, either MPI or in a PGAS language, can be useful even if you're running on shared memory machines, is to avoid that kind of problem. So I guess in some cases, more sophisticated scheduling and load balancing is useful if your algorithm isn't dividing up work evenly. And this one, I wouldn't have guessed that this was a problem because it is dense. They are dense matrices, so I would have thought they would be evenly divided. But because they're relatively small matrices, if you've got a block size that doesn't divide evenly into the matrix dimension, then you're going to have some load imbalance at the end of that, where there's some processors that have sparsely populated, or not, incomplete blocks, and that you can end up wasting time relative to the percent of peak. Any questions? I'll probably have to defer them to. Okay, so there were a lot of optimizations, and finding the optimum required a lot of trial and error, so I think probably everybody learned that, even regardless of how much performance you got out of it, although probably even more for the people who tried a lot more of the optimizations. The performance models that you use, I mean, things like the roofline model are very helpful to give you a kind of a guide of, how fast should you be going? Are you close to the optimal or whatever? But they don't really tell you how to optimize the code. So they won't tell you what block size to have or anything like that. So in particular, I think that if you picked a block size that was exactly equal to what fits in the cache, that often is not quite the right thing to do. In fact, there's sort of there was sort of a trend in a lot of the papers. There were a whole bunch of papers written called tile size selection, and I don't think I mentioned this at the time when I was talking about this optimization of tile size. But there are a lot of papers that looked at the question of how do you choose the optimal tile size when you know something about the architecture and you know something about the microarchitecture, right? The low-level details of the cache size, and there often was a fudge factor in those those papers, they would sort of say, well, you know, we calculated the optimal tile size was X, and we decided, and the best one was actually X over 4 or whatever. So, you know, it can be somewhat mysterious as to what's probably getting stored in the cache and therefore knocking your data out of cache. For optimal performance on real applications, you know, the best thing to do if you can get access to them is to use optimized libraries. So I'm sure you all appreciate that. And people got really different performance on the different machines. So any questions or comments? Or okay. Hopefully, did you learn something from that whole thing, homework one? Okay, let's talk about sparse matrices, and I'm going to start by just kind of reminding you, there's a little bit of reminder of what sparse matrices look like, and we'll talk about the format, and then mostly I'm going to talk about sparse matrix vector multiply today. I'll talk a little bit about other cases. So, you know, here's some, there's a duality between a graph and the sparse matrix representation of that same graph. So here's some pictures of very different kinds of sparse matrices and the graph that's associated with them. So this is a linear programming problem. Linear programming problems tend to be very unstructured. They're not necessarily square. They're not symmetric. This one is a structural design problem. I think this one is both square and symmetric, as is the internet connectivity, of course, because if something is connected to, they're not directional edges on these in this kind of a graph. So the internet is, you know, is a two-way connection on each one of those edges. So, but you can just see visually that each of these matrices have very different sort of structure in them, and so that's going to be a theme when we try to figure out how to optimize the matrices, is understanding something about the structure. So. Specifically, sparse matrix vector multiply is almost surely the most common kernel that comes up in any kind of a sparse matrix algorithm. There are other kind of algorithmic kernels on sparse matrices that are also important, but things like sparse matrix, and I'm just writing it out here, sparse matrix, dense vector multiplication, so SPMV, as it's usually called, comes up in solving linear systems, so Krylov subspace methods, eigenvalue solvers, optimization algorithms, machine learning algorithms, and so on. So they tend to be iterative algorithms. They're going to repeatedly apply sparse matrix vector multiply over and over again across some number of iterations, and with, in many cases, the same matrix structure used across iterations. And sometimes the values change, sometimes the values are the same, but you're just multiplying it by different vectors. Okay, so that's what will be what we'll mostly talk about today. You can also do sparse matrix sparse vector multiply, and that comes up in certain graph algorithms, and Aiden will be lecturing a little bit late next week, I think, a little bit later on graph algorithms, and we'll talk about some of these you know, sparse matrix kernels as they're used in, say, the graph laws library and other the comp laws library and things like that. And so I won't say a lot more about sparse matrix sparse vector multiply, but it does come up in these other kinds of problems. And sparse matrix multiply, which is often called SPGEM, just because sparse matrix multiply is kind of a mouthful, and other ways of writing it out is a little bit confusing as well. They also come up in graph algorithms, so I think Aiden will probably touch on both of those when he gives that lecture. There is a common case that comes up in a lot of other kinds of algorithms, numerical algorithms, which is multiplying a matrix times its transpose. So A times A transpose comes up in both machine learning kinds of problems. It comes up in simulation, you know, various kinds of solvers and so on. Okay, another one that comes up is sparse matrix dense matrix multiply, and I will say a little bit more about that because there was some recent work by one of my students on sparse matrix dense matrix multiply for graphical models calculation that is used for and so a machine learning algorithm. And we'll see how much time we have. If I have time for that, it's a little bit optional. Okay, so important, you know, lots of kernels, but let's focus on mostly on sparse matrix dense vector multiply, SPMV. So just to remind you, here's a common format for a sparse matrix, compressed sparse row. For those of you who have undergraduate majors in computer science and took a data structures course, you learned about something like an adjacency matrix representation and adjacency list representation for a graph. That's what this is. It's an adjacency list representation. For every row, every vertex in the graph, we're going to store a list of all of its edges, right? So that's exactly what we're doing in this sparse matrix representation. So when we program these, especially in Fortran, but also just if you're trying to have really efficient data structures, you tend to not use pointers. You tend to use packed arrays of things. So we have 3 arrays. The value array, which is the list of floating point values typically, if it's a floating point matrix, that all the non-zeros that are in the matrix. So you can see the red, the 4 red ones all packed together and the green ones all packed together and so on. And then the index array, so those are going to be integers that tell you what column that non-zero came from. And then to figure out what row it came from, you store a 3rd array, which is shorter, which is just the dimension of the matrix that shows you where in those longer vectors, in both of them, each one of the rows starts. So from that you can calculate what every value is in the matrix. And this is optimized also for the fact that we're going to use things like sparse matrix SPMV. So we're going to use these. We're going to do matrix vector multiply on these kinds of matrices. So those are the pieces of it. And well, let me just stop here because it's really important that everybody's got this really in their head. So if there's anything that's unclear, please ask now, because otherwise you'll be lost in the rest of the lecture if you don't kind of have this ingrained in your mind as to what this looks like. Okay. All right, so there are other common formats that come up. Compressed sparse column is one. I'll mention a little bit about that, and you'll see why it tends to not be as common. There's coordinate format, which is where with every non-zero you store a row and a column index. So you've got more indices stored with a coordinate format. On the other hand, a coordinate format, it's not necessarily sorted, and so it's a great format if you're going to be constructing a matrix on the fly a lot. Like if you're spending a lot of time constructing the matrix, you can just sort of append non-zeros onto the end with their ij coordinate and not worry about how exactly where it lives relative to other things. Obviously, pretty cumbersome in terms of multiplying it because everything is kind of bad things happen in the memory system when you've got things unordered like that. But that one is another one that comes up. We'll talk specifically about blocking and what blocking looks like in these matrix formats as well. Okay, so let's see. There's also I wanted to comment on this. There are hundreds of matrix formats that people use in practice. So why do they use all these different formats? Because as you saw from the pictures, the little spy plots I showed you, there's often some kind of very special structure in your matrix. And for example, if you've got diagonals that contain a constant value in them, you might separately store those diagonals and just compress them so that there's just one value and it just says, oh, the diagonal is here, and it starts here and it's this long or whatever. So there's all these different reasons why you might have some kind of a matrix format that's very specialized to your problem. And as a result, and I think I'll make this comment later, but as a result, a lot of libraries that provide iterative solvers that use sparse matrix vector multiply will allow you as the user to define your own matrix format and then to define your own SPMV, and they'll kind of do all the other numerical stuff on top of that, but it'll use a kernel that you've written. Okay, so what does matrix vector multiply look like in code on a sparse matrix stored in CSR format? So this is the same picture as before. I'm multiplying a times x to get y. I like to draw x like this at the top, even though, because then you can see that each one of the values of x needs to be used, multiplied by the thing below it in order to calculate the value of y. And so, we're just calculating y sub I is equal to y sub I plus aij times xj. The problem is we have to figure out where is the x value that we need. So here's the loop that says for each row I, we're going to get the pointer out. Remember that tells us where to start. So the pointer k tells us where to start in those two arrays, and then up to the next place where the row ends, which is the start of the next row. And then we're going to just calculate y sub I by multiplying the value that's at wherever k is pointing to right now, that index, times x of index of k. So we're looking up the column index. That tells us which one of the x values we need to pick up, and then we just multiply that together. So again, any questions? Or if you need to think about it, tell me to stop, because you really also kind of want to have this in your head. So this is a BLAS2 operation, matrix vector, not matrix matrix. that means that you're not going to see any kind of performance numbers like you saw on the previous slides for homework 1. This is, even if it weren't sparse, we wouldn't see anything like that because there's just not that much reuse in matrix vector. It's also sparse, so there's going to be extra data around to move around. So there's no reuse of A, right? You use every element of A, which is a pretty big data structure, exactly once in doing a matrix vector multiply. And that means you're reading all the values and all the indices once. The pointers you're going to reuse multiple times, but you're going to read it into a temporary there. And if we organize this as we have, we've got a compressed sparse row format, and we're going to write the code in this way, where we're running through the rows and computing a dot product, a sparse dot product on those elements. Then we've got the maximum reuse of Y, the elements of Y, all the way across the row. And in fact, we could pull Y out and put it into a temporary. So we'll talk about that. If it's sitting in the level 1, Y sub I is sitting in the level 1 cache, you're going to get hits on that all the time, even if it's not in register. Now, so the only kind of thing that's obviously wrong here is reuse of X. So do you get any reuse of X? Well, it's going to depend. By the time you go around the corner and you find another non-zero that's in the same column that you were in the previous row, is it going to still be in cache or not? Well, it depends. This is a really tiny matrix, but imagine you've got a really, really wide matrix. By the time you go around the corner, that value of X that you read in order to get the non-zero above you may no longer be in cache. Yes?
So is X a dense vector, or how?
Yes, sorry, yes. X and Y are dense vectors, and then A is sparse. So that's why you can just, you just look up the index value that tells you what column index it's in, and then you can look directly, just do a regular old array lookup on X, and that gives you the value that you need. Okay. Any other questions? Okay. All right, so what are some things? This is the same code again, so I haven't changed it, and there's just showing you the data structures so you have them, you can look at them for reference. So what are some things we could do? Well, we could unroll the K loop, so in order to unroll the K loop, we kind of need to know how many non-zeros there are in a row, right, if you're going to actually unroll it. So you might need some extra code around there to deal with that. You could unroll it some number of times and things like that. You can hoist Y sub I out of that inner loop because Y sub I is, Y sub I is not going to change when you're up here, so you can make it temporary for Y sub I outside of the inner loop. It says, okay, absent aliasing. What does that mean? Well, Y sub I is being written to. Hopefully, somebody hasn't passed in a result vector Y that somehow overlaps with your, your matrix or some weird thing like that, which would give you all kinds of, funny stuff. So the point is, though, that for a compiler, very hard for it to figure out that it can necessarily hoist it because you got all these arrays around it and it doesn't know whether they're aliased. And this thing right here especially confuses the compiler because it says, I have no idea where you're accessing an X. I can't look at that index expression and say anything about it. Now you as a programmer know, oh, those are integer values that are, by the way, consecutive. They go up, they're not consecutive, but they're increasing within every row. And so within that loop body, you know that you're never going to have the same value of index sub k when you're in one iteration of the outer loop, right? Within one row, you never have a non-zero in the same position. You know that, but there's no way a compiler can figure that out by looking at the code because it's stored inside the data structure. Could you eliminate the indirection? Well, you may, if you know something, if you've got a really special matrix, and this is where you'd probably come up with a different format, then you may be able to get rid of that level of indirection. If you know that, for example, you've got diagonals and you're going to just store the matrix by diagonals, then you don't need to have this indexing necessarily in every element. And we'll look at a way of eliminating it some of the time. Can you reuse the elements of X? Well, you need a good non-zero pattern. And so you can think about two different cases. As you know, the cache is going to take care of this automatically. So when is the cache going to be friendly if you've got non-zeros in nearby rows that are in the same column, right? So if they're in the same column, when you come around to that another row, hopefully that value of x, which is read-only, right? You're just reading x, you're writing to y, that it's going to be sitting in your cache. And so that can be helpful, and so for a lot of matrices, you'll find that you do get pretty good cache reuse because you've got non-zeros that are in some kind of a pattern, for example, clustered along the diagonal. That means that you've got a high chance that by the time when you get to one of those non-zeros, it's going to be in a column that was already accessed from a previous row. Okay, but if you got non-zeros spread all over your matrix and it's a very wide matrix, then by the time you wrap around the corner, you probably have knocked the x values out of cache that you care about. Because it won't just be on the next row, it'll be a few rows down that you'll hit the same, you'll need the same x value. Okay, and what about registers? Well, what if you want to, now in software you want to control exactly which values x are and that you're going to reuse them. Well, then you really need to know what the structure, where the non-zeros are, so you as a programmer can figure out how to save the value of x sub I or x sub I plus 1, x sub I minus 1 using some spatial locality. So we'll talk about that, and it's going to be related to blocking. So what is it going to look like to register block for a sparse matrix? But as written, you really, there's not much you can do for register blocking. Okay, questions? Okay, so I'm repeating a couple slides here that Sam Williams gave, I think, at the end of his roofline lecture, just because I think at the time that he gave it, we hadn't really studied sparse matrix vector multiply. So this is a roofline model for 4 different machines, and here's some of the, you've got these 2-unit stride streams, so that's really good for the memory system. You've got the value array, and you've got the index array. So you're going through those linearly in memory, and so hopefully any reasonable memory system is going to be good at prefetching those 2 streams. It doesn't, you don't need to worry about this random access thing. So the only place where you've got the random access problem is in X, but the val and index arrays are going to be unit stride. It's inherently a fused multiply add, or does a multiply add in the inner loop. So it's the best thing for basically any hardware that is optimized FMAs, which is pretty common. That oftentimes, as you know, you can go twice as fast if you're doing a multiply add. So we'll be happy in terms of the instruction level, the floating point operation that you get to use in the inner loop. There's no instruction level parallelism. There's no data level parallelism as written. Floating point performance is about, what does that say, 12 to 25% of the instructions, I think. And the flop to byte ratio is less than 0.2. So and that's just looking at how much data do you have to read in order to multiply this matrix, assuming that your x vector, by the way, never vacates the cache. So just in the best case, so this can be a useful model to think about, which is just to say, well, let's assume I always hit in my x vector, but I have to read my entire matrix, which has got both an index vector and a value vector, and then I can compute from that, and I know how many flops I have because I know how many non-zeros I have, and that's my rate. This is, by the way, being for simplicity, this is done with a dense matrix in sparse format. So this is also going to be the best case that you'll ever get from a real matrix, most likely, maybe modulo some caching effects. Okay, so here we are. There's our roofline model, and we're well, okay, in this case, our computational intensity is so low, we're at the roofline because the roofline is, very, very low. And in general, we're kind of close to that bottom number of the bandwidth number, but that's because we're not taking advantage of any kind of NUMA effects, which is what will help us get to the higher bandwidth number. So we can optimize for NUMA, and I won't go into some of the details, but you gotta worry about your different your memory channels and maybe how to do manual prefetching, and that bumps you up to that green line, so you get up to a higher point on the on each one of those roof lines. So these are somewhat old processors, but this one is, and this was a cell processor, right? Remember PlayStation 3, I think, and Los Alamos built a supercomputer out of it. I think partly based on Sam's results that said you can run things like sparse matrix vector multiply on that processor. So, okay, so let's try to do some more interesting optimizations. Now we're going to actually change the matrix format. Okay, so this is not, so before all the optimizations we talked about, well, not so many of them, but the things that Sam had applied there were things like prefetching and stuff, and maybe, you know, kind of changing the loop structure, the code generated, but not really changing the matrix, at least in any fundamental way. Okay, so what is register blocking all about? Well, we're going to try to change the format. And here's a picture of a real matrix that is called Rafsky 3. I'll zoom in and into the upper left so you can see what it looks like. So it's obviously a very well-structured matrix. All the non-zeros are clustered around the diagonal. It has this sort of tri-diagonal pattern, although the distance between those is not just one. It's not just one away. So there's a little bit more structure, probably because it's from some other kind of I don't know, problem with more structure in it. So, so this is what happens if we zoom into that little, one of those diagonals. Okay, so one of those diagonals is not just one set of non-zeros, it's actually a whole bunch of non-zeros. In fact, they naturally fall into these little 8x8 blocks. And so that's great because we can now take advantage of that in our matrix format. And so a lot of people, this comes up pretty frequently in, say, finite element problems. Number of degrees of freedom you're looking at will give you some dense substructure on your sparse matrix, even if your kind of overall structure is pretty irregular. You'll often have some kind of dense sub-blocks inside of it. Now, as a user, if you're taking the class and you say, oh, I've got these dense subblocks, let me just write matrix vector multiply to optimize for those 8x8 blocks. And what we'll find is that's not necessarily the right thing to do, even if you have them. But what are we going to do? What does it mean to take advantage of it? Well, the bottleneck in sparse matrix vector multiply is entirely about the time to read the matrix. So because we've only got 2 floating point operations per non-zero in the matrix, and the non-zeros, to fetch them, we have to get a column index and we have to get a floating point value. I'm ignoring the pointer into the row values here because it's not such a large overhead probably. But we have to at least get one float, say a double precision floating point value if you're doing 64-bit, or and a single, say, 32-bit int or something like that. And we only got 2 flops. So rather than storing a column index for each non-zero, we'll instead store a column index just for a block. So we'll basically store what column that block starts in, and then everything else in there we can just compute by an offset. And so as the block size grows, the total amount of storage that we need can grow by as much as can shrink by as much of a factor of 2. That's assuming that we're doing, say, single precision floats, so you've got equal amounts of indexing overhead as our actual values. You can't get rid of our values, right? Our values are our values, so you need the floating point values in there, but you're just trying to shrink the indexing overhead. And so that'll decrease the total amount of time it takes to read the matrix. We're changing the data structure and we're changing the algorithm. This is a pretty expensive sort of optimization to do, not something a compiler is going to do for you typically. I think there's a few research papers that try to do this automatically, but it's it's really mucking around with the data structures in a way that could really break the rest of your application unless you know what you're doing. So, and in this case where we had that nice matrix, that nice dense structure, is 8x8 actually the best choice? It looks like it probably is because it minimizes the storage. And again, we're here in these numbers I'm going to show you, we're going to look at the dense matrix and sparse format as kind of the best case, not that Rafsky matrix. Oh wait, this one is actually the Rafsky matrix, sorry. I'll show some other numbers that are dense matrices in sparse format. So it turns out that 8x8 is indeed faster than the unblocked 1x1. It's 1.5 times faster, but it's not the optimal. The optimal is over here, which is 2x4. Okay, so it's something that fits within that 8x8 block naturally, but it isn't the maximum size. And that could be because you don't have enough registers on this particular machine in order to actually hold, the values you need. Now, you don't need to hold the whole block, but you do need to hold the x and the y, subpieces of x and y. You need to do the little local matrix vector multiply. So So that tells us that we might need to search around for these, as you did somewhat manually probably in your homework assignment. And these are looking at, oh, these are still Rayski numbers, so this is that same really well-structured matrix, and just showing you, these things in terms of where's the optimal block size does change. So here's the, I think, so there's a different Itanium processor in which it's 1x4, here's the 2x4 case, there's a 4x4 case, and there's a 1x4. So they all, not surprisingly, fit inside of the 8x8 block, but 8x8 is not optimal. I think here's a case where actually it does become optimal on that, the Ultra 2i processor in the upper left there. So, different processors are going to give you different blocking, which is what you found also in homework 1. So, okay, so that was an easy case, although we still have to kind of figure out what is the right block size, even if we know we've got 8x8 dense subblocks in our matrix completely uniformly throughout the matrix. But what really happens in practice is we often don't have such nice structure. So here's a finite element problem, and it's got a somewhat more complicated non-zero structure. There's a little bit of statistics on the matrix. I'll again zoom in on the top upper corner of this. So here's what this matrix looks like. So not so obviously blocked, but what we can do is we can say, well, what if I tried to block it? And so I'm going to, by trying to block it, I'm going to put a kind of a logical grid over it. In this case, I'll try blocking it into 3x3 blocks, and 3x3 is actually going to be the right thing to do in this case, but I might have tried a whole bunch of different possible block sizes. So if I think about putting this grid down, and I say, well, if I were going to block this in 3x3, I'll only store one index per block, so I've got a factor of sort of 9, decrease in the total number of indexing overhead I have. Obviously, my floating point numbers are still there, but I'm going to add something now, because in order to actually get those blocks, what I'm going to do is fill them all in with zeros. So I'll add explicit zeros into the matrix, and this seemed, actually, when we first tried to do this, we thought this seemed like a crazy idea, because you're actually adding 50% more kind of non-zero entries into the matrix. Now they're actually non-zeros that happen to have the value 0, but we're going to store them in the matrix. So it seems like the matrix is getting bigger, and the amount of computation we have to do, the flops, is also getting larger. And so you have to do more work in this. So why is this a good idea? Well, because you've actually shrunk the index set by that factor of 9, and overall, even though you've increased the fill overhead is 50%, it actually runs 50% faster, at least on this on the Pentium 3 processor that we originally did this on. So, and if you did a dense matrix in sparse format, the kind of theoretical speed up here for such a matrix in which you're filling it in by, if we didn't have any zeros that are getting filled in here, what this says is I could get up to a factor of 2.2 by going with a 3x3 blocked matrix rather than going with a 1x1 block, or sort of the default CSR format on this particular processor. Okay. So, okay, so that was a little bit surprising that we can put that many zeros in, and we're going to do floating point computations on them. And notice that I'm talking here about runtime. I'm not talking about floating point rates. When we do talk about floating point rates, we'll have to be careful to only count the blue flops, right? We're only going to count the flops we have to do, not the ones that we're making up in order to fill this in. Okay, so Sam says, okay, well, let's do some register blocking. Now we've shifted our computational intensity over a little bit, because we have shrunk the size of the matrix, and so the total bandwidth that the flops don't change. As I said, we're going to do extra flops, but we're not going to count those in this calculation. And then we're shrinking the size of the matrix. So we shifted over, and we get indeed some improvements. There's also a bunch of things that happen that kind of benefit that come from the fact that we've got little register blocks now. We can optimize that code. We can get that, the CS267 homework group that decided to write assembly code, and we can get them to write assembly code for a little teeny tiny dense matrix vector multiply, because at that point it's dense, right? That's all we need to do in a dense sublocks. And so we can figure out what the best way is to write little tiny matrix vector multiplies, not matrix, so it's not still going to go as fast, but dense matrix vector multiplies, and then put them into the code. And that's kind of what Sam did. And now he's getting some reasonable performance, by the way, on the cell processor as well. So, okay, well, we kind of like to have a library for these things so that we don't have to call them. And as I mentioned earlier, well, if you're using, and those of you who are looking for project ideas, if you do want to do something with sparse matrices and you want to use a very sophisticated library for things like fluid dynamics or structural engineering or whatever, there's a couple of libraries like PETSI and Trilinos that will provide you with built-in solvers, but you may have to write and optimize SPMV for a particular machine that you want to run on, such as Cori and maybe Cori Phase 2 with the KNL processors or something like that. But they do kind of call-outs in order to allow you to do an optimized SPMV. But if we wanted to build an optimized matrix library that provides SPMV and maybe a few other kernels, well, how are we going to do that? Well, that's what OSCE did, the optimized sparse kernel interface, which was originally built by Rich Vuduk, based on some of the results that I just showed you, and based on a previous student, Yunjin Im, who did some of the kind of by hand optimizations and figured out how to optimize this. So, and there's more on this on the web pages for the Bebop group if you want to see it. Okay, and there's OSCE, our favorite bear. Okay. Okay, so what are we going to do? So this was the idea, at least in both of their PhD theses, which were a few years apart here. But the idea is we're going to try to pick the right register block size. So I'm just going to focus on register blocking. We'll also assume that with register blocking comes a bunch of other optimizations, low-level optimizations that you can do that will boost your peak performance. So what we'll do is we'll take a dense matrix and sparse format. So the problem is we don't know what matrix you're going to hand the library in advance, right? So what we'll do is we'll say, well, at the point that somebody installs OSCE on, say, the Cori system, so some neurosystem administrator installs OSCE for you, for us all to use, they'll go and run dense matrices in sparse format as part of the installation process. And from that, they're going to compute a megaflop rate, well, is it megaflops at the time, gigaflop rate, whatever you prefer, which is the rate at which, for that blocking factor, the matrix will, that sparse matrix vector multiply will run. Okay, so we've got highly optimized code inside of the inner loops, and we've now done in this sort of offline fashion, before somebody hands you a matrix, we're going to compute a table that says, given a blocking factor of, say, 3 by 4, this is the megaflop rate you can expect to get on this machine. And then at runtime, we're going to estimate by looking at the matrix, and we could do this precisely if we didn't want to, if we weren't worried about the amount of time it would take. We're going to figure out how much would we have to fill in the matrix. What is the fill overhead required to put the matrix into that format? And so you calculate the fill overhead for a bunch of different block sizes. You multiply that times the megaflop rate, or divide it anyway, to figure out what would be the estimated performance of that particular matrix running this format, because all that fill is going to make it run a certain fraction slower. And so we'll just try to minimize this estimated time based on the fill overhead divided by the megaflop rate. And let's see, so this part we do once for the machine, this part we do once per matrix, although we can also build in, and OSCE does this, it can remember some history of what you ran yesterday. And so if even if you're not running exactly the same matrix, but you're running a matrix that has similar characteristics, because you're, by the way, running structural engineering problems that always have, whatever, 6 degrees of freedom or something, then you have the non-zero structure that looks similar. It can remember that that's the right block size to use based on that. Okay, so this is what a profile looks like for the dense matrix in sparse format. These are just all the running times. So this is now, we're computing it over a much larger column block size, but you can see that on this particular processor you want a pretty small column block size. Sorry, both column and row block size. And it isn't at all symmetric, because we're doing this calculation across the rows, and you're really trying to get reuse in these registers. There's different operations in the 2 dimensions. Okay, so let's see. Let me just skip this. We're going to this shows you for a bunch of real matrices, and these are what does it say? Rich Vudek's thesis matrices that were in here there, but a lot of them come from places like Matrix Market, which is a standard sparse matrix benchmark suite. If you end up with a project looking at sparse matrices, it can be a good place to look for examples. And they're kind of divided into finite element problems. There's the dense matrix in sparse format. There's a finite element problems with some variable coefficients in it. Linear programming problems, which tend to be the worst in terms of the structure. Remember, you've got these kind of rectangular matrices with the non-zeros that are spread out all over the place, and then other stuff that didn't fit in one of those categories. And that's the performance that you're getting from trying all of the possible blocks, register block sizes at least that are reasonable, say up to 12 by 12 on this particular machine. And so the question is, how well does the performance model do at predicting that that's the best one? And the performance model, it tells us to use a block size that gives us, even if it might be off in terms of the block size, but it gives us performance that's pretty close to the best possible. So performance model actually works quite well in this case. And by the way, how well does it do relative to a dense matrix in dense format, DGEMV? You know, still this is going to be well below the well below peak, because it's still a bandwidth limited problem to do a dense matrix vector multiply, or because it's still BLAS 2, but that's the performance up here. And so you can see that the dense matrix in sparse format is at least approaching the dense matrix in dense format. So that's good. It's using a big enough block size that the overhead doesn't matter too much. You know, here's what happens if you look at, so cache blocking. So that was all about register blocking. Maybe I should stop there and just say, any questions about register blocking? Okay, so I'm going to fill in little dense blocks so that I can reduce the indexing overhead, and that's going to, in many cases, and in fact I would say in Sam Williams' thesis, which came later, his conclusion was if you just optimize for the size of the matrix, that total storage used in the matrix, that's a pretty good heuristic. I think that in one of the earlier examples I showed with the 8 by 8 blocks, that was not the optimal block size, but it's often the case that what you're mainly trying to do is you're trying to shrink the matrix. Okay, so what about cache blocking? Well, you're familiar with cache blocking. Turns out cache blocking is not nearly as useful for sparse matrix vector multiply. We don't have as much use and much reuse, sorry, in the algorithm, and so we thought it was going to be a great idea, and Rajesh Nishtala in his thesis looked at this, and this is a cache blocking a matrix from latent semantic indexing, and these, you know, you do see some benefits here from cache blocking. But he actually went on to write a paper that's called When Cache Blocking of Sparse Matrix Vector Multiply Works and Why. And the reason the paper is titled that is because in many cases it did not work. And what you find is you need a matrix that has pretty non-uniform sorts of non-zero patterns. Otherwise, you're going to your cache hit rate in the X vector. Remember, that's the only thing we're worried about is cache hits in the X vector is going to be pretty good. So there's no advantage of cache blocking if you're hitting in the X vector and hitting the X vector is hitting the cache. It needs to be wide enough that by the time you go around the corner, the thing is no longer in cache. And so you end up having these kind of matrices that are wide and look kind of non-uniform there, that have a random non-zero pattern where you get the biggest speed ups. So anyway, that was the conclusion of that work. Okay. Now, the other thing that you can do, and this will come up again, and you'll have another lecture on this later, is matrix reordering. So one of the things we can do is we can look at the matrix structure, and we can try to permute the rows and columns. And for a lot of algorithms, that's going to be a safe thing to do as long as we remember that we've permuted them. And we can then reduce we're going to improve the cache hit rate in the X vector. So there's, by the way, all the things that we can do in terms of memory optimizations, and this is looking at kind of a case study of accelerator modeling design. So you've got this big accelerator, particle beam accelerator, and you're trying to design it, and so this will be an example of a matrix that comes up in that case. And I'll talk about, so it's going to be a symmetric matrix, which I haven't really talked about, does complicate the indexing in the algorithm. So it sort of seems like it's completely obvious in terms of if you've got a symmetric matrix, you'll only store half of it, but now your indexing does get more complicated. And we'll look at how you can reorder it, and there's some details on the reordering algorithm, but we're going to use, I think, something called reverse Cuthell-McKee. So this is kind of the matrix as we first look at it. It does have some structure. You can see the non-zeros clustered along the diagonal, but there's a lot of stuff that's off diagonal. There's a little bit of other sort of block structure in the matrix. So if we do a reverse Cuthell-McKee reordering, which is going to try to walk through the matrix and cluster things near the diagonal, looks much better. Okay, so once we've done this reordering, our cache hit rate should improve quite a bit. There again, actually in Yunja's thesis many years ago, she looked at this ordering and found that for serial processors it tended to not make a big difference. It may have had to do with the size of matrices that she was looking or how unstructured they were, that if there was still enough kind of good structure that you're getting a good cache hit rate on the X vector, then it may not matter, but it can make a big difference, especially when we get to multi-core. But here's what we're really doing in this particular case is trying to get we're trying to get the non-zeros clustered around the diagonal so that we can do register blocking. And so this is what, after if I blow up a little piece of this matrix, and now I look at what the structure looks like closer, as I zoom in, it does have this kind of structure, and I can now go through and fill in we can fill in some explicit zeros. So we put in the, let's see, we're doing some reordering, and so we've gotten the red things clustered, moved in closer to the diagonal, so we don't have those. Plus we can now fill in explicit zeros, which are the green ones, and then give us little dense subblocks, which will make it go faster. Okay, so and this is how fast that, on this particular matrix, what kind of speed ups you get doing. So when Aiden talks about graph algorithms, you'll see that one of the applications of those graph algorithms will be reordering matrices in order to improve their locality. So let me just say briefly, you do have to remember that you've permuted the matrix, and for a lot of algorithms, you can take these permutation vectors into account and permutation matrices, and you can solve the problem on the permuted matrix. You just have to remember how to unpermute it at the end. Okay, so let me just not go into details on that, because I do want to talk about distributed memory, which we haven't really talked about yet, and some other communication optimization techniques. So what are some of the optimizations we've seen for sparse matrix vector multiply? Actually, haven't really done multi-core very much either. We saw register blocking as sort of the main thing. There's something called variable block splitting, where you can take a matrix and look at it as a sum of two other matrices, each of which might have much better structure. You can store the non-zeros as diagonals, so rather than storing a position as a column and row index, you can store it as a diagonal index and then just store the contiguous set of things if you've got a bunch of long diagonals that are stored in the matrix. You can do reordering, take advantage of symmetry, cache blocking I talked about. I didn't really talk about multiple vectors. That one's actually very important, because multiple vectors, if you're multiplying, which often comes up in various algorithms, you see this in machine learning, why does it go fast when you're doing deep learning, is because you're multiplying something times a bunch of vectors, and now it starts to look more like dense matrix multiply, or at least sparse matrix dense matrix multiply when you've got the multiple vectors. So maybe a kind of a tall skinny matrix, which I think Jim talked about last time in the dense linear algebra lecture, but you can when we've got a set of vectors, even if it's not a huge set, when you're down at the register block level, now you can really get some decent performance out of those small matrix multiplies that you're doing. There's other kernels besides SPMV, such as sparse triangular solve. There's an optimization that comes up in those. It's called switch to dense. If you're solving a tridiagonal matrix, oftentimes the lower piece of it is pretty dense, and so you might just want to use you just want to fill in all the zeros and use a dense algorithm for some piece of it, but you don't want to do that for the entire matrix. And there's other higher level kernels, one of which I'll talk about a little bit later. So I mentioned before, there are a bunch of algorithms that use something like A times A transpose or A transpose A or whatever in there in these. And if you have a kernel like that, then there's more potential for reuse, because now the whole idea is going to be, can you read the matrix A once and actually compute something like A times A transpose without reading A twice? Okay, because we're bandwidth limited. Okay, questions about those optimizations? Okay, so let's look at multi-core first. There's lots and lots of different ways that you can do them, but I'll just talk about kind of a pretty straightforward way of parallelizing it, which would be row parallelism in SPMV. So here we've got our matrix again that's sparse. We've got our result vector. We've got our x, our source vector that we're multiplying by. If we do row parallelism, then that means a processor here gets a set of rows, and so it has to do random access into the x vector, which on your shared memory multi-core system may be a little bit slow, depending on exactly where X lives, but that, it is what it is, and that'll work on shared memory hardware. You don't have any inter-thread dependencies because only one processor is writing to a particular element of Y. You may have to worry about some false sharing in here, which would be the performance issues, but you don't have any data races and you don't need any locks, okay, because only one processor is accessing a given element of Y, which is the only thing that's being written in this particular algorithm. It's probably obvious, but if you've got a sparse matrix structure that's not uniform, you don't necessarily want to divide up the number of rows evenly. You want to divide up the number of non-zeros evenly to give you good load balance. And so that's another trick that you're going to play. So what if you were to try writing this in column parallelism? Well, it's just useful to think about that, and you may want to look at it for certain kinds of problems. And in fact, if you're doing machine learning, this kind of looks like a little bit like model versus data parallelism, right? For those of you, I don't know why they, anyway, made up different terms. I guess they're a little bit different, but this is like our model that's being updated here, and so if we compare, what happens if we divide this matrix up by columns, which would then divide X up by columns? We'd keep those aligned, and we let Y be a big shared thing in shared memory. Well, now we've got random access. We have two problems, and the reason we don't even use this in the serial case is because you have twice as much memory bandwidth. You have to both read and write Y, whereas in the CSR case, where we're running down the rows, we only have to read and write Y once, and then and you only read the values of X. So we double the memory bandwidth, at least for that vector, not for the whole computation. But probably more importantly, we need to synchronize. And so we need to synchronize because now we have lots of processors that are all potentially trying to write to the same element of Y. And so that's the reason that we tend to not do that. Now, there are cases where we're going to want to combine row and data parallelism because it'll give you more total parallelism, especially when you get to a larger machine. Okay, so what happens with SPMV performance? Again, some numbers from Sam looking at but now running on multi-core nodes, and these are a few different processors. So this is just the purple down here was just naive serial code. That's what it means. It's just serial code. Maybe the compiler is doing something for you automatically, but there's nothing being done manually. And now there's p-threads, so some explicit parallelism, threaded parallelism in the code, it certainly speeds up by about a factor of 2, but this is but not as much as we would like. I think this is an 8-core system. So now it's really the same optimization ideas, but now we're going to apply them in a multi-core setting. Cache blocking may be more useful here because we're worried about false sharing and things like that. So now the performance goes up by this is just putting the different things like register blocking, which he calls compression. By the way, compression is not just register blocking, also does things like uses narrower data types such as 16-bit ints for storing your indices, because within a block you don't need that much range for an index. So as long as you can kind of remember that I've stored an offset in the X vector, and I just need to know kind of how to add that 16-bit value onto whatever my global offset is in the vector, then I can store smaller indices for each one of my index values in the matrix. So there's ways that these are basically techniques though for compressing the matrix. And there's some heuristics that are used to try to minimize the memory traffic, and then let's see. You also can add some software prefetching. So the numbers do definitely go up. A cell blade processor is still not, you have to really program that quite differently, so it's still performing pretty badly. Now we do some other memory optimizations. This is cache blocking and TLB blocking. So that's the orange, which you see almost no benefit from in any of these. There's a little bit for like the linear programming matrix. Remember those wide, very sparse, kind of random access pattern sort of matrices, you do see some benefits from cache blocking. But now if you manually go and optimize for this cell blade processor, you can get it to outperform all the other processors at the time on this calculation. And this is the kind of speed up that you get from combining all those optimization techniques together. That's the average speed up across a lot of different matrices. Okay, so can we put this stuff into OSCE? Well, we call this POSCE for parallel OSCE, and it does have some automatic heuristics that are built in for things, and it's got some of the standard routines such as sparse matrix vector multiply. By the way, we would be happy to have students work on this for a class project. This was something that was done a few years ago and hasn't even been run, as far as I know, on the latest hardware, but it would involve trying to take the software and get it to run and look at what these different optimizations do on modern architectures such as the Knight's Landing machine and so on. But it has plugin extensibility, and I believe it has been put into the Trilinos library as well. I don't know if it's still in there. There's a lot of other optimizations that could be added. So there's a little bit more complicated architecture of POSCE but it has the same ideas of trying to be able to remember something about, it's building these benchmarks that are based on dense matrices in sparse format, but it can also remember something about the matrix that you've used, and you can use that sort of history in doing optimization, so you don't have to do a full auto-tuning kind of search on every time you use it. Okay. So that's sparse matrices, as I said, or sorry, that's multi-core, and as I said, mostly the techniques there are the same as they were for serial code, but you do end up with somewhat different performance results. So what about distributed memory parallelism, since you're now MPI programmers? Well, we've got the same kind of problem here. I can do row parallelism or column parallelism or whatever. So if I do row parallelism, what does this look like? Well, let me assume that the y in row parallelism like this, that the y vector is partitioned across the processors. So every processor has its own piece of the y vector that it's going to update, doesn't need to communicate with any other processors for the y vector. So the only problem you have in terms of writing this code for MPI communication is how to access the x vector. And one thing to keep in mind is in a lot of iterative algorithms, the x vector is not necessarily identical to the y vector from the previous iteration, but is often computed from it. So you don't necessarily get to pick your layout as saying, oh, I would like the x vector to be laid out, replicated, for example, across all the processors, because it comes out of a previous iteration in some way. For example, partitioned across the processors. So if we've got row parallelism, and we're assuming that y and a are partitioned, then we're going to replicate x across the processors. That's the simplest thing to do, at least the simplest thing to think about is just broadcast, every processor broadcasts their own piece of x if they have a piece of x, and then you're sure that everybody can do their local matrix vector multiplies with that value of x. Now you can be more clever and only exchange the necessary pieces of x depending on your non-zero structure. If your non-zero structure looks like this, probably no benefit by trying to be clever, because almost every processor is going to need every one of the values in x, is going to need every one of the values of x, because we've got our non-zeros spread uniformly. Every processor needs every value of x. But if you've got non-zeros that are clustered around the diagonal, for example, or even clustered sort of anywhere in the matrix, then maybe there could be a significant savings. For example, you could have a matrix where there's entire parts of this matrix that are completely empty, right, are completely zero, and then you don't need that part of the x vector. So, but that's the way you write this code for distributed memory. You can also use column parallelism, and in this case, and this also will look familiar to those of you who maybe are thinking about parallel machine learning algorithms, but now I'm going to assume that x and a are partitioned, so I've got my lines going this way. I'm going to make a temporary copy of y, which is actually going to be zeroed out initially, and it's going to be I'm going to call it delta y, which is the part to add. I'm going to do compute updates, matrix vector products for everything that I now own, everything in a block column. So I just look at that little piece of the x vector, I multiply it times everything, and I update my full copy of the y vector, which has got a bunch of zeros in it, and may even have a bunch of zeros in it at the end. And then I do a big reduction operation at the end that sums all of those y vectors together. Okay, and I can also do something more clever where I pack them and things as I did for the row case. But we've got to do a reduction now. I am changing the order of the add operation, so I'll get slightly different results numerically than I would in the other order, but it should still work fine. And I can do 2D parallelism, where I do both column and row parallelism. And this tends to be useful when the non-zeros are uniformly distributed, as in this kind of cartoon of a sparse matrix. So imagine that I take my processors and I divide them in a P1 by P2 grid. It could be squares, so it could be square root of P by square root of P. And then I'm going to run basically one of the algorithms across the rows and the other algorithm across the columns. And I'm going to do that by thinking of my MPI ranks as teams. So I'm going to use like a team of processors that's all working in a block row like this, and they'll run a little column parallel algorithm within that team. Okay, so there's a couple of benchmarks, and I'll show some results from one of them. An older one is called the NAS-CG benchmark. It's a conjugate gradient and iterative solver algorithm based on matrix vector product and dominated by matrix vector product. I think there's some other reductions and so on in there. And that benchmark used a random non-zero pattern for the matrix. And so what that meant is that people who were optimizing for that benchmark tended to use a 2D partitioning of the matrix, even though for real problems that come up in, say, modeling and simulation, where you've got some structure in your matrix, that's typically not the right thing to do. So what's the problem with the 2D partitioning? If I've got I've got my zeros non-cluster, I've got my non-zeros cluster around the diagonals, I got a bunch of processors out here with nothing to do because they may have completely empty blocks. Okay, so you can try to be more careful about how I partition things, but that's basically that's what the problem tends to be. But a 2D parallelism, when you've got a pretty uniform non-zero structure, it can be a very good thing to do. It can give you much higher levels of parallelism, right? The limit on parallelism up here is the total number of rows. The maximum P is equal to n, the total number of rows, and for this one it's m, the total number of columns, and so I can get much larger parallelism if I use both kinds of parallelism. Okay, so now perhaps I'm just going to remind you of the graph partitioning idea, because maybe it's even more obvious now that we're doing distributed memory parallelism to think about this. So I'm once again, I've got my processors that are divided up here by rows. So I've got a block row algorithm, but imagine that my x vector is also partitioned by in the same size chunks, perhaps because it came from the y vector from a previous iteration, so it now looks like kind of the transpose of that. I guess, yeah. So, well, what's a great matrix for this? Well, a great matrix would be all of my non-zeros are in these little green blocks right along the diagonal. And then if all my non-zeros are inside there, I actually don't have to do any communication. I can compute these independently. So that's a really nice property of the matrix. And so what you'll do is to run a graph partitioning algorithm that will try to cluster the graph into sort of cliques or strongly connected pieces of the graph, p different pieces of the graph, so that I can reorder the matrix and make it look kind of like this. And I'll have some parts of the non-zeros that are out here that will involve communication now, but now I've got a smaller amount of communication if I can get most of my work inside of those, and most of my, if there are not a lot of non-zeros out there, each processor will only need a subset of the x values from another processor. Okay, so we'll talk about that. We'll talk about techniques for graph partitioning. Okay, there's a relatively new benchmark called HPCG that comes from Mike Haru at Sandia, is really the lead on the Trilinos project, does a lot of work on libraries, numerical libraries for sparse matrix-based algorithms, so SPMV kinds of things, and Jack Dungera, who was also involved in and is involved in the original top 500 high-performance LinPack benchmark. So this is going to be there's a benchmark here that is doing conjugate gradient. I won't talk more about numerically what this is doing. I'm sure some of you are very familiar with it and some may not be, but the main point for this purpose as a performance benchmark is it's going to do a lot of matrix vector multiplies. And they've set it up in this somewhat, it's a somewhat structured sparse matrix because it's really a stencil matrix, and it turns out you can then write it either as a kind of structured grid code or as a full sparse matrix code. And since Jim will be talking about structured grids, he may mention this as well on Thursday, but we'll just look at what some of these top machines look like in terms of the HPCG benchmark. So these are the fastest top 10 machines in the world from November on the HPC benchmark list, and this shows you the rank on the top 500 list. So the LinPEC, dense matrix multiply limited versus basically memory bandwidth limited. So there's some network performance that comes up in terms of memory latency for computing the CG computation, but a lot of it is going to be about how much memory bandwidth do you have across the machine. So some of the fast machines are still fast machines here, and you can see things like the Cori system, and this is the Xeon Phis. It's 8 on the top 500 list and 7 on this HPC CG list. Similarly, some of these other machines are kind of at very similar places. There's some pretty big reordering. So the K computer, which is a special purpose architecture built in Japan with a high-speed network called the Tofu interconnect and these Spark 64 processors, that's ranked number 10 on the top 500 list, but is ranked number 1 on the HPCG benchmark. So if you really care about memory performance and network performance, this benchmark can give you somewhat, maybe it gives you a better idea of how it will run. You can also see, though, what fraction of peak these are running at in terms of this is relative, the guaranteed not to exceed hardware performance of the machine. How fast is HPCG going? So the best number up there for that for the Japanese, the Riken machine is a little over 5% of peak, and the others are all under 2% of peak. That's kind of what that benchmark looks like. Okay. So the last topic, I'm going to skip the next topic actually because I want to make sure I get to the very last topic. I'll just mention briefly that recent work looking at machine learning algorithms for graphical model calculations does use some ideas for optimizing sparse matrix, dense matrix multiply. So now you're multiplying a sparse matrix times a dense matrix, and you may think, well, if the dense matrix is dense, then it completely dominates everything else. And indeed, sometimes you just want to move the sparse matrix around, but it depends because the dense matrix may be tall and skinny, it may be a different, have a different shape, and so that leads to a bunch of different optimizations. And so this is work by Penpor and Cohen-Anticool, and it's been applied to brain imaging analysis. So if anybody's interested in a class project related to machine learning of this kind for graphical models, let me know and I'd be happy to talk to you about it. And I'm sure Penpor would as well. She's off at Google though now. Okay, so the last topic I do want to talk about in more detail is communication avoiding iterative solvers, which are built on top of sparse matrix vector multiply, or at least that's kind of the natural way to think about them. So this was a graph from a number of years ago looking at where does the execution time go in sparse matrix vector multiply. And the important thing is and this is after optimization, so we've got Yunjanim, we've got Rich Fudik, we've got Sam Williams, whatever people have done their best work to try to optimize sparse matrix vector multiply either by hand or maybe OSCI has done it for you or POSCI or whatever. And what you should end up with at that point is something that is dominated by the time to read the matrix. So these red pieces of the bars here are just saying if I just look at how much time is going into reading memory, then it's pretty substantial. I mean, it's not completely dominated on the Itanium 2, but here for the other machines is a pretty big piece of the running time. And even on that machine, we're not going to get more than a factor of 2 speed up, right? Because we've got to read that matrix. And there's also a performance model behind this that says, if you just say, what I'm running at the peak memory bandwidth of this machine, what is the estimated amount of time? And it looks similar to this. So that says, in fact, I think the red bars get even larger. So that says, we're now kind of doomed, right? If we're trying to optimize, in fact, that's what we were doing at the time. We were trying to optimize sparse matrix vector multiply, and we realized, well, we better not put any more PhD thesis students on that topic because we've now saturated the memory bandwidth limit, and you're not going to go any faster unless you can come up with clever ways of compressing your matrix, which there is still work going on in there. But modulo that, we're kind of done. So the question is optimizing sparse matrix vector multiply the only thing we can do if we're interested in these iterative solvers that are going to apply SPMV over and over again? And this just says kind of what I've already said. We're memory bandwidth limited, so can we beat this bottleneck? So the truth is that we're going to do many SPMVs, not just one. And so in, for example, Krylov subspace methods that are doing this kind of iterative solvers, we can look at the fact that we're doing a sequence of these matrix vector multiplies, and what we're going to do is try to compute AX, A squared X, A cubed X, and so on, all at once with one read of the matrix A. And there's some other things, I think Jim talked last time about TSQR, some of the other parts of these iterative solvers where you're are also going to use that algorithm as well. But for this lecture, we'll just talk about the SPMV. So the question is now, if I want to read the matrix once, and I want to compute k factors of AX, A squared X, and up to A to the k times X with that one read of the matrix A, how can I do it? Well, for the purposes of this illustration, we're going to take a really, really simple matrix, okay? And we will generalize it later, but we'll take a tridiagonal matrix. And what I'm showing here is we start out with X. We're going to multiply A times it once, then A squared and A cubed. So what do the dependencies look like? Well, for this particular value of AX, I need the two values that are next to it because it's a tridiagonal matrix, right? So that's what the dependencies look like. I don't know that as a compiler, by the way, but inside, if I knew what the matrix structure is, I would know that's what it looked like. So it's got that little dependence. Now, similarly, at some other part of the iteration space, if I had A squared X, I could compute A cubed X by just knowing the two values, the three values right below me. And so if I had these, 7 values, I can get that one on the top. And so now you can see a pattern growing, and we can compute this parallelogram, this trapezoid by getting a larger set of things on the bottom. It's got an extra k things to the left and the right relative to what I'm trying to compute out the top. So in a serial case, the way I can think about it is on the left-hand edge, and I'm not worrying about the boundary conditions here, I can start with these values, and I can kind of at each step compute a set of values that's one smaller on the right-hand edge. Now, if I've done that already, for the next one, I can use a parallelogram. I can pick up the next set of things. So the idea is this: not only does this x value, set of x values fit in the cache, but the values of A, which are really associated with these edges in the matrix, right, those non-zeros that were in the tridiagonal matrix, I can fit those in my cache too, or my fast memory, right? So I will now walk up and I can compute that set of things. And similarly for step 3, and then I can finish things off in step 4. Okay, so that's what the sequential algorithm looks like. And the idea is that I've only read the A matrix, those non-zero values in the matrix once, but I've managed to compute, in this case, A cubed times X with that one value. Because I've read a block of it at a time, a piece of it at a time, and then and then can slide over so that every time I'm reading it, I read a block in that I can, or some piece of the matrix in, and that'll come up later, then we can compute these other sort of pieces. So what about a parallel version of this? Well, now think about our X vector being partitioned over the processors, and I'm not showing the matrix edges in here, but they're really implicit in the dependencies. So now I'm getting for processor 2, if it gets some extra stuff, it gets 3 extra values on each side, similar to the parallel algorithm. And remember, X is read-only here. We can compute A cubed times X with that set of values. Okay, so there's a little bit of redundant work in the way this algorithm is run with that extra stuff that hangs out the edge, but that's kind of the way each processor can do some redundant work and get pretty good locality, because it can get a piece of the A matrix and a piece of the X vector that live inside of its own local memory, and its own, say, L1 cache that's not shared with any other processor. So that's kind of what the overall picture looks like in terms of what the processors are computing. These triangles down below are the redundant parts of the computation. And so this algorithm works pretty well if you have a matrix that is pretty easily partitionable. And so But what does it look like if I don't have just a tridiagonal? So this was the easiest possible matrix, right? A tridiagonal, well, maybe not quite the easiest, but almost. So what if I have a more general matrix? Well, here it's useful to think of the graph structure of the matrix rather than writing it out as a sparse matrix format. So what am I trying to do? I'm trying to compute the set of values inside of this yellow region at each one of those vertices. So that might be a to the third or fourth, I think, a cubed times x. And remember, the a values are the weights on those edges in the graph. So I'm going to need some values of the A matrix in addition to the initial input x that's in there. And so now what do I need? Well, in order to compute a times x, not only do I need the stuff that I'm going to end up with, but I need kind of one set of neighbors, one level out. If I'm computing a squared x, I need 2 levels out. A cubed times x, I need 3 levels out. So now we need to do some fancy graph partitioning. And once again, Aiden will talk more about it. But for general matrices, you do have to you have to run some graph partitioning algorithms in order to figure out how to get this to work. This does speed up, at least on a multi-core system. This was work by Mark Homan. I think I lost the reference. It was on this slide. And by Margub Mahoiden, who did a lot of the low-level optimization work. And so there's the speed-ups for computing a to the k times x rather than sparse matrix vector multiply k times. That's what the comparison is. And this is gigaflop rate, so up is good. So the top of the green bars is the performance that you get for the a to the k kernel, and the red one was what you started with for just SPMV, and for a bunch of different matrices across the x-axis. And there's a bunch of performance modeling. Let me just show you what happens when you put this into a solver, and this one is in particular going to be put into GMRes. You can prove, by the way, that you're doing optimal data movement in this case as well. Similar to what Jim talked about, probably for dense linear algebra, but it's a fairly different kind of argument here because of the sparse, because of the iterative solver. But now there's something that we have to worry about. We've changed the numerical computation, right? So it used to be that I would do a times x, then I would do a bunch of other stuff that I'm waving my hands about today, that are going to compute some dot products and so on with the vectors. And now I've kind of, as a compiler person, I think of it as reordering the loops. So I'm taking all of the a times x's and kind of putting them together. And so I have changed the order of the floating point operations. And so when I take this communication avoiding kernel, we stick it into our iterative solver called GMRes, bad things happen. It no longer converges. So fortunately, Jim and others, his students, so Mark and others, looked at the GMRes algorithm and realized that if you use a different basis, it's called a different basis, so it still uses the same basic kernels, you can actually get convergence back. So the high level point from this, and you can go read the paper if you're interested, is if you're going to muck around with the higher level algorithm above the SPMV level, you probably are going to be changing the floating point arithmetic ordering. And once you do that, you do have to worry about whether you're getting the right answer anymore. And so you need to be sophisticated about it. But you do get some real advantages in terms of performance by using these higher level kernels. And this is looking at so the purple and blue here are basically the sparse matrix vector multiply versus, and this is relative runtime of the code, and this is the sort of everything else that I didn't talk about very much, which actually has TSQR inside of that orange piece of it. And so you do get some speed up again on this multi-core system. Lots more work that could be done here if people are interested. So let me just kind of end with the takeaway messages. You know this, tuning for modern processors, even single processors, is hard. Sparse matrices are even harder. Matrix vector SPMV is, the benefits of tuning it are lower because the computational intensity is low, and you can use some of these standard tricks that you've already used for doing dense linear algebra, but you may have lower benefits. Things like reordering and compressing the matrix are important, and if you've done a good job of optimizing, SPMV should be memory bandwidth limited, and that's why you might want to look at higher level optimizations at that point if you're trying to get more speed. So with that, I will end. Any questions? Okay, thanks very much. As I mentioned at the beginning, I think Jim will talk about project ideas as well as probably Ben will talk about homework 3 next time. So you want to come?